Every day, our sky is hijacked by a localized nuclear furnace. The sun dictates the temperature of our atmosphere, drives our weather systems, and blasts us with a continuous stream of raw, blinding energy. But when the Earth rotates away from that glare, the sky reveals thousands of other stars. Without the daytime interference, they appear as a spray of faint pinpricks, some glowing brighter than others. To categorize those pinpricks, the ancient Greeks created a ranking system. Today, we call it apparent magnitude. It is a strictly observational, logarithmic scale that measures exactly how bright a celestial object looks to a human standing on Earth. Because of how the math is structured, brighter objects get lower and even negative numbers. The absolute faintest stars we can spot with the naked eye sit at a magnitude of +6. The Sun, however, registers at an overwhelming -26.8. Based purely on the sensory data collected by human eyes, the conclusion is obvious. The Sun is the unrivaled, towering center of the cosmos. But that perception relies on a massive geometric blind spot. Apparent brightness is a trick of perspective. The light hitting your retina is the product of two colliding variables: the star's actual power and the vast empty space that light had to cross to reach you. As light travels outward in a vacuum, it spreads over the surface of an expanding sphere. If you double your distance from a light source, the exact same amount of energy is now stretched across 4 times the area. Triple the distance, and it's spread across 9 times the area. The intensity drops by the square of the distance. Because of this inverse square law, a faint point of light in the night sky could be a massive high-wattage bulb located incredibly far away, or it could be a dim, low-wattage bulb sitting right next door. From Earth, without additional data, they look exactly the same. To understand what a star actually is, we have to measure its true, intrinsic power output, a metric called luminosity. This is the total energy the star pumps into space every second. To strip away the visual illusion of the night sky and calculate that true luminosity, we need the one variable our eyes cannot perceive. We have to figure out the exact physical distance to the stars. For the closest stars in our galactic neighborhood, astronomers solve for distance using a geometric technique called trigonometric parallax. As Earth moves through its orbit around the Sun, our vantage point shifts by a distance of 1 astronomical unit. If we take a picture of a nearby star and then wait 6 months to take another, that nearby star will appear to wobble back and forth against the static background of much more distant stars. Eventually, distances become so vast that this tiny parallax wobble is impossible to detect. For deeper space, astronomers rely on standard candles, objects like pulsating Cepheid variables and Type 1a supernovae. These are cosmic beacons that explode or pulse with a known, predictable luminosity. By stacking these techniques, using parallax for the local stars and standard candles for deep space, astronomers constructed a distance ladder. And once the distance to a glowing object is locked down, we can calculate exactly how much power it is actually generating. This formula strips away the illusion of perspective. The distance modulus links apparent brightness to actual physical distance. Isolating capital M gives absolute magnitude, a star's brightness if we removed distance entirely, lining them up side by side. To make a fair comparison, astronomers established a standard cosmic baseline. We calculate what the sky would look like if every star were placed at a distance of exactly 10 parsecs, which is about 32.6 light-years away from Earth. Pushing the entire stellar population to this 10-parsec line acts as a great equalizer. It forces every celestial object to compete purely on its own physical output. If we run the thought experiment and physically push the Sun back from its cozy distance of 1 astronomical unit out to that 10-parsec baseline, its dominance evaporates. Stripped of its home field advantage, the Sun's magnitude plummets from a blinding -26.8 down to a +4.8. At that distance, it is reduced to a faint speck, barely visible to the naked human eye. Now we do the reverse. We pull the rest of the galaxy's stars in, snapping them to that exact same 10-parsec line. Stars like Sirius, which are already bright in our sky, become blistering. Massive giants like Betelgeuse would cast harsh shadows on Earth, blazing thousands of times brighter than our local star. The sheer energy gap is staggering. The Sun emits a continuous 3.8 times 10 to the 26th watts of power, but the heavy hitters of the universe, the supergiants, expel up to 1,000,000 times that amount of energy in the exact same second. Stripping away the trick of distance reveals the Sun's true status as a middle-tier G-type star, a completely standard unit of energy, drastically outclassed in size and power by the galaxy's true titans. This chart maps out that exact hierarchy. It's the Hertzsprung-Russell Diagram, plotting visual magnitudes against color indexes, which correspond to stellar luminosities and surface temperatures. Notice the heavy diagonal band slicing through the middle. That is the main sequence, representing the long phase where stars fuse hydrogen into helium in their cores. Our Sun sits squarely in the center of this band. It is classified as a G-type dwarf, a completely standard middle-of-the-road furnace. The incredibly luminous monsters occupying the upper left of the chart are actually quite rare. If you sample a random volume of space, the vast majority of stars you find are red dwarfs, objects that are even smaller, cooler, and dimmer than our own. The Sun is special to us only because it is close, but looking at the cold math of the cosmos, its absolute averageness is its greatest feature. By being a quiet, stable dwarf, it provided the steady radiation and the billions of years of calm necessary for us to evolve and look back out at the sky.